Titrations are a common form of chemical analysis carried out in chemical laboratories. Despite the advent of sophisticated spectroscopic forms of analysis, the simple titration is still the preferred method of analysis for many analytes, including the determination of the acidity or basicity of a solution. In a titration, a standard solution is used to determine the unknown concentration of a solute in a second solution. And a standard solution is a solution where we accurately know the concentration of a particular solute. A titration involves the gradual addition of the standard solution to the unknown solution until the solute of the unknown solution has been completely reacted. It's important to note that the solutes of both solutions need to react in a known way. And in acid-base titrations, for example, we're already very familiar with that type of reaction because we know that an acid plus a base gives us a salt plus water. And if we were given the identity of an unknown acid, for example, phosphoric acid, and we knew the identity of a base, we can now write a balanced chemical equation for that. So let's say, for argument's sake, we wanted to determine the concentration of phosphoric acid in a solution. And there we've got our phosphoric acid solution sitting in a beaker. Now remember, the purpose of a titration is to determine the unknown concentration of a solute in a solution, in this case phosphoric acid. We start by accurately preparing a known volume of the acid. And so in this case we're going to say that, let's say for argument's sake, we have 20.0 milliliters of phosphoric acid accurately known in this beaker here. We then gradually add a base until all of the acid has been neutralized. We know that bases neutralize acids, and we know that acids and bases react in a specific and known way. So let's just say, for argument's sake, that the base we used was barium hydroxide solution. What we would then do is we would add barium hydroxide solution to the phosphoric acid solution until the acid has been neutralized. Now it's important to note here that the solution that we add is a standard solution. We know the concentration of it accurately. And let's again say, for argument's sake, that the concentration of the barium hydroxide solution is 0.100 molar. So we know it fairly accurately. The final thing we do is we record the volume of the base added until we get to that neutralization point. In acid-base titrations, the neutralization point, or the equivalence point, is determined by the use of an acid-base indicator. Initially, the solution is acidic in nature. As we neutralize the acid and keep adding more and more base, we'll get to a point where we have complete equivalence. There's no net acidity, no net basicity. One more drop of base, that solution will have a net base, and that acid-base indicator will change color. So here's the scenario that we've got experimentally. Down the bottom, we have a known concentration of acid, 20.0 mils of phosphoric acid. In the burette above, we have our standard solution of barium hydroxide, a 0.100 molar solution. And the burette is used to deliver a known volume of solution. Now what we're after is determining the concentration of the phosphoric acid solution. So molarity equals moles over litres. And we know that we can express that as moles over 0.020 litres because we already know what the volume of the phosphoric acid solution is. We know we've got accurately 20 millilitres down there, and that 20 millilitres converts to 0.02 litres. So all we have to do now is calculate how many moles of phosphoric acid are in those 20 mils. And to help us do that, we start performing the titration. So we start gradually adding in the barium hydroxide solution until we see a colour change. Then we turn the burette off and we record the volume. So let's say, for argument's sake, it took 26.4 millilitres of barium hydroxide, the standard barium hydroxide solution, 0.1 molar. It took 26.4 mils to react with our phosphoric acid solution. What we need to be able to do now is generate our balanced chemical equations. All of these solution stoichiometry calculations are based on balanced chemical equations. So we've got our acid plus a base. We know that it gives us salt plus water. We can just write the water formula down straight away. So the trick here is trying to identify the salt and then balance the equation. The salt is going to be an ionic compound. We're going to take the metal from the base and we're going to take the non-metal anion from the acid. So we'll put the barium and the phosphate together there. So barium phosphate is the identity of the salt in this particular reaction. We've got to ask ourselves, is this the correct chemical formula for barium phosphate? Well, barium is a group 2 metal. It has a 2+ charge. Phosphate is a polyatomic ion with a 3- charge. Clearly, these two things won't come together in a 1-to-1 ratio. If we do our crisscross method, we'll take the 2 from the 2+ charge of barium and bring it down as the subscript for phosphate. We'll take the 3 from the 3- charge of phosphate and bring it down as the subscript for barium. And we get Ba3PO4 being the chemical formula for barium phosphate. So we'll stick that in there. The next thing we have to do is balance this equation, and in balancing the equation we'll see if I put a big 2 out the front of the phosphoric acid, a big 3 out the front of barium hydroxide, and a big 6 out the front of water. We now have a balanced chemical equation. 2H3PO plus 3BaOH2 produces Ba3PO4 plus 6H2O. Let's look at the information now that this titration has given us. The information about the barium hydroxide solution is that the reaction required 26.4 millilitres of 0.1 molar barium hydroxide solution. We also know that we were given the information that the phosphoric acid solution, the volume of it, was 20.0 mils. And what we're being asked to calculate here is the molarity. So this is now starting to look familiar because we can go to this diagram here, and the relevant part of the diagram is this right-hand side over here. We've been given the volume and molarity information about barium hydroxide, and we've been asked to find the molarity of the phosphoric acid solution. So we use the volume and molarity data of the barium hydroxide, and we calculate the moles of barium hydroxide in step 1. Step 2, we calculate the moles of the phosphoric acid solution by using the ratio of the stoichiometric coefficients. And then step 3, we will find the molarity of the phosphoric acid solution using the volume information that's been provided. So, step 1, moles of barium hydroxide will equal molarity times litres. Remember our molarity equation, molarity equals moles over litres. That can be rearranged to make moles the subject. Moles equals molarity times litres. So moles of barium hydroxide equals molarity of barium hydroxide times litres, and we get 0.100 molar times 0.0264. So the 0.100 molar we were given, that's the standard solution. We accurately knew its concentration. We deliberately made it up at 0.1 molar concentration. The other information we've been given is the 0.0264 litres. This comes from our 26.4 millilitres, and we've just done a unit conversion from millilitres into litres there. When we plug those two numbers into the calculator, 2.64 by 10 to the minus 3 moles of barium hydroxide. Step 2 is to calculate the moles of phosphoric acid using that information. So the moles of phosphoric acid, the moles of H3PO4, equals 2 on 3 times the moles of barium hydroxide. And the 2 on 3 is the ratio of the stoichiometric coefficient. We've got the stoichiometric coefficient of the substance we've been asked to find information about, divided by the stoichiometric coefficient of the substance we've been given information about. So 213 times 2.64 by 10 to the minus 3, that number there was calculated in step 1. When we put that into our calculator, we get 1.76 by 10 to the minus 3 moles. So the final step now, step 3, we're calculating the molarity of the phosphoric acid solution. Molarity equals moles on litres, and we've just calculated the moles of phosphoric acid in step 2, and we already knew the volume of the phosphoric acid solution because we controlled that as part of the experiment. We knew it was 20.0 millilitres, and we've just converted that into litres, 0.0200 litres. When we put that into our calculators, we get a concentration of phosphoric acid of 0.0880 moles per litre, or 0.0880 molar. So the concentration of the original phosphoric acid solution, 0.0880 moles per litre.